Welcome to this lesson in which we're going to look at terminal velocity, which is something that people often get confused about, so I've decided to give it its own video. Okay, so first of all, the idea, before we go into terminal velocity, what we need to understand is frictional forces. And these are things such as air resistance, friction between surfaces, and drag. So this could be like in water or in fluids, for example. Air resistance is like, for example, if you're running and then you run faster and faster, then you suddenly feel like there's a lot of wind blowing at you. That is not actually wind, but rather because wind is when like a bunch of air comes towards you, right? Essentially, just like fan your face and then you'll feel some wind. But then air resistance is when you're going through the wind, so it's as if the wind is coming at you. So it gives you the same feeling essentially. But if you're just walking, you wouldn't really feel any air resistance, or maybe we're kind of already used to the air resistance, so we don't really feel it that much. There is still a bit though. However, the idea is essentially that the faster you move, the more air resistance you're going to feel. So with air resistance and also with drag is like, let's say you're in water, there's going to be a lot of drag when you try to swim or something like that. If you're moving faster, you need to go through more air particles or more water particles, and then that's going to cause you to feel more frictional force. So that is the idea of frictional force. As for friction between surfaces, that is a slightly different idea, but it's like, let's say you have an object on a slope. It doesn't fall down. It doesn't fall down because even though like there's a part of the weight is making it try to slide down, that's because there's some friction between the surface of the object and the surface of the ground, which is causing it to still stay up. So friction between surfaces, that also depends on what the surfaces actually like are. For example, if you had grass, there would be more friction than if you had like ice. So that would be a case where you didn't have a lot of friction. So those are things that you can take into account. Usually a question will say like, you assume air resistance is negligible or something like that. So if it does say that, it means you don't need to take into account any effects of air resistance. But you could like see a question where it says air resistance is not negligible or air resistance is significant, or assume there is air resistance. And then in those cases, you would need to consider the force of air resistance. So we're gonna take a look at how to do that. And that is the idea of terminal velocity, or terminal velocity is a common idea in which they try to test your understanding of air resistance, essentially, which you might have also been familiar with from IGCSE. So terminal velocity is the idea that you're gonna drop something, right, on the earth. And so there would be the effect of gravity. But then aside from the effect of gravity, there's also the effect of air resistance because it's going to fall through air. And the graph that you usually see is this one here, where we have velocity on the left axis and then we have the time on across the x-axis. So what we're going to see here is the velocity of the object starting off from 0 because it's starting from rest, like we're dropping it. So in the beginning it doesn't have any velocity, but we're going to see it accelerating at the greatest rate in the very beginning, and over time it's going to slow down and reach a terminal velocity. So this plateau is called terminal velocity. After that, usually the situation we have is that this is like a person falling and then they have a parachute. So they're going to open a parachute, and then what's going to happen is they're going to slow down until they reach a new terminal velocity over here. And then when you see this final drop off is when they reach the ground and land. We're going to go into the different parts of the process a bit more here. We're going to consider the forces essentially. In the very beginning, there isn't any force acting on it except for its weight. So the resultant force, which I've tried to show with this purple arrow, is going to be the force acting downwards. Because of that, it experiences an acceleration downwards, which is equal to g. So acceleration is equal to g here in the very beginning. However, after a while, it's going to increase in velocity. So as it increases in velocity, what's going to happen is that it's going to experience more air resistance as well, right? So here, this arrow upwards, A is the air resistance upwards. In the beginning, however, when it's not moving that fast yet, so maybe around this region, the weight is still going to be greater than the air resistance, so the resultant force is still going to be downwards. And so it's still going to be accelerating downwards, but the effect of the acceleration is going to be less as in there's going to be less acceleration. That's why the gradient is becoming less steep. Eventually, though, we reach this point where, which is called terminal velocity, which is where the weight downwards is equal to the acceleration, is equal to the air resistance upwards. So in this one here. And that means that if W is equal to A, there is no resultant force, and so it is no longer accelerating. It is moving at constant velocity, which is where it's reached terminal velocity here. So that's when it's gone flat. After a while, when you open the parachute, so what is the point of the parachute essentially? The point of the parachute is that it has more surface area, and with more surface area, it's gonna be hitting more air particles. If it hits more air particles, then it's going to experience more air resistance, like when it's moving at the same velocity. So the problem with this now then is that with more surface area, it's going to experience much greater air resistance. So the air resistance is going to increase, but the weight is not going to increase. The weight is going to stay the same, which means for the first time, we actually have a force acting upwards instead, because the effect of the air resistance is greater than the downwards weight. Here I've written A plus L. That's because we have the original air resistance from when it didn't have a parachute, plus the extra air resistance from the parachute, which I've represented with the letter L. So in that case, we're going to have it decelerating, which is why the velocity decreases over here. And then you'll see that the deceleration is a curve like this, not to be confused with a curve like this. The reason it's a curve like this is because over time, as it slows down, the effect of the air resistance is going to decrease as well. So the air resistance is actually going to decrease as the velocity decreases, causing the deceleration to also decrease. So we have decreasing deceleration in this region, which hopefully you guys remember from the velocity lesson. Finally, we reach a point where the air resistance upwards is equal to the weight downwards once again, but this is going to be at a lower velocity. Because it's already slowed down quite a lot. So at this point, the total resultant force is 0 and there is no acceleration, and it's continuing to move at a constant lower velocity, which is considered to be safer. So the person lands on the ground with this safer lower velocity. And so when it lands, it just goes right down to 0 because you just landed, so you're not moving anymore. So that is terminal velocity. So that is it for this lesson. I'll see you guys in the next one where we'll look at momentum.